This video is not for anyone who doesn't like feeling like a grain of salt in the entire universe. So we know the universe is big, right? Like exceptionally big. We can now measure the estimated size of the observable universe to about 96 billion light years across. This is wider than the universe is old. But before we get to that, I want to take you back in time to the days when Einstein was working on his general theory of relativity. It is the 1910s and we are only now just discovering how big the universe truly is. Now, this was a time, kind of the golden age for astronomy. We were starting to figure out what stars were made out of, the fact that there were so many different types, and starting to investigate these pesky things called nebulae. Now, nebulae or dust clouds had been catalogued for literally hundreds of years, and to the naked eye through smaller telescopes, they look pretty similar, like clumps of dust and gas scattered throughout our galaxy. But we started to build more sophisticated telescopes and more sophisticated instruments to really determine what some of these nebula were. While these investigations were going on, Einstein was working hard in his laboratory to do the incredibly challenging math of general relativity. Now, general relativity is an incredible set of equations which outline exactly how space and time are one and how they interact with mass. Mass bends space and time, and in turn, the bent space and time tells matter how to move. All of this was done by Einstein assuming the universe was static, with what we saw in the night sky being it. That we lived in the universe, but our universe was just our galaxy. And it's important to remember, we had no idea we were living in a spiral galaxy yet, just the stars on the sky. These equations didn't quite work though without a constant being put in to stabilize for a static universe. And what Einstein had no idea he was doing was actually describing one of the most mysterious phenomena in the universe, dark energy. We'll get to that later on. So we've entered the 20s now. We have incredibly precise math that seemingly explains the fabric of space and time. And Edwin Hubble is working incredibly hard to try to figure out exactly what were those fuzzy patches of nebulae on the sky. Hubble was using something called a Cepheid variable to be able to figure out exactly how far away were these lumps of dust and gas. These were discovered by Henrietta Leavitt, and without them, we might not know what we do about the universe today. Using these variable stars, they could take the period of variability and figure out its direct luminosity, making it much easier to calculate distances across space. And this worked excellent for our very nearby galaxies. What Hubble found was quite shocking. The universe wasn't static, it was in fact moving, and moving bizarrely. It seemed most galaxies measured were moving away from us. And this was later described as Hubble's law. This opened a whole can of worms because all of a sudden our universe was a lot more dynamic than we had even predicted. Through decades of hard work from astronomers all around the world, we were able to build up a better picture of exactly where we were in the universe. And it appeared in every direction we looked, there were endless amounts of galaxies. As astronomy got more complex and we started using charge-coupled devices, we could take more data of the sky than previous astronomers could even dream of. With this data came more hardcore science. We were able to then use dying stars to measure distances more precisely. And when we did, we shocked ourselves. The universe wasn't just expanding, it was accelerating. And up until this discovery, there was a huge debate on exactly why the universe was expanding in the first place and if it could possibly stop. In the midst of all of this hard work over many decades of time, the Big Bang Theory was formed, but that is a video for another day. Now we've travelled in time to about the 1990s, but there's some other surprises waiting for us too. As larger astronomical surveys were conducted, our count of galaxies was increasing exponentially. Again, the universe was looking pretty endless. And thanks to the speed of light, we can use this to look back in time. So we think our universe is accelerating, but what on earth is causing it? This is where we go back to Einstein and his helpful cosmological constant. And it seemingly describes the negative pressure dark energy has on the universe. Now, what we've come to understand is that dark energy appears to be constant when we model it, meaning we think it is built into the fabric of space and time itself. What is truly remarkable and sometimes a little mind-boggling is that the amount of dark energy isn't changing, it isn't increasing, but its effects are just felt a little bit more. This is because as space and time expands, there is less mass in total acting on any given region of space. And we start to move from a matter-dominated universe to a dark energy-dominated universe, meaning that push outwards by the dark energy has more effect than the pull inwards due to the curvature of space and time. And this is equally neat and insane, because if we keep modeling it, the universe will eventually run away with dark energy, meaning at some point in the very, very, very distant future, the universe will be accelerating faster than the speed of light, and matter will no longer be able to hold itself together, and this is when the universe will die. But this will not happen anywhere in our human lifetimes, which means we've got a hell of a lot to explore. The observable universe that we can theoretically see is about 96 billion light years across, meaning we literally have trillions of galaxies to interrogate and figure out exactly how our universe is made. Now, trillions of galaxies is a very big number, but it just gets bigger when we start to think about the fact the universe could very well be infinite. So far in physics, we haven't described what is containing our universe, if there are any bounds, and if those bounds have any constraints. The theory of general relativity seemingly works excellent on the scales we can measure, but we will never know for sure what is beyond our observable universe. Because we are limited by the speed of light, the speed of information, there is just no way for us to be able to tell. We can come up with theories, and everything from multiverse to contained universe to living on the back of a turtle. But ultimately, and what really gets to me, is that we just have to accept that the universe just is. That the physical laws will remain to hold true, and we will probably never know all of them.